Hello, this video includes information on hydrolysis of salts.
Okay, well, we know about acids, strong acids and weak acids, and we know about bases, but what about salts? Okay, well, salts are neither acids nor bases by definition. So they don't have hydrogen as their positive ion, and they don't have hydroxide as their negative ion. But they can have acidic characteristics. They can change the pH of the solution. So let's say that we have 0.100 molar sodium hydroxide, which is a base, and we add it to 0.100 molar hydrocyanic acid, which is a weak acid. Okay, well, we're going to produce sodium cyanide and water. It's essentially a double displacement reaction. The sodium here and the hydrogen here switch places. Now, sodium hydroxide's a strong base. That means it's an electrolyte. So it would break up into its ions in solution. But hydrocyanic acid is a weak acid, which means it pretty much stays in its molecular form. It's not breaking up into its ions. Sodium cyanide is a salt, and it's an electrolyte. It's going to break up into ions. Remember, anything with an alkali metal in it breaks up into ions. And water is going to stay in its molecular form. The sodiums are spectator ions. We could cancel those out. They have no effect on the pH of the solution. But the cyanide ion does. And the way the cyanide ion affects the pH of the solution is cyanide is the conjugate base of a weak acid. So it's going to go through a basic ionization reaction. The cyanide that was produced is going to react with water to a very small degree, but it's going to react with water. It's going to produce hydrocyanic acid and hydroxide. And because we increase the hydroxide ion concentration, the sodium cyanide is a basic salt. So let's look at a calculation. Okay, we have 0.100 molar sodium cyanide. Okay, the first thing we want to do is write down what happens when we put it into water. Okay, well, the sodium cyanide is going to break up into sodium ions and cyanide ions. It's an electrolyte. The sodium ions are not going to affect the pH of the solution, but the cyanide ions are. So we're going to write our basic ionization reaction. So we've got the cyanide ions, which came from the sodium cyanide, reacting with the water. The water is going to act like an acid. It's going to donate its proton. We're going to produce hydrocyanic acid and hydroxide. The hydroxide is going to increase. The hydronium ion is going to decrease, and the pH is going to go up. Now, we can write an ice chart. If we have 0.100 molar sodium cyanide and it completely breaks up, we have 0.100 molar cyanide ion. Okay, a little bit of it is going to ionize in water. We're going to produce X amount of the hydrocyanic acid and X amount of hydroxide. We can write, and I kind of skipped this, I should have written it, sorry. We can write a KB expression, I should have done that. So HCN times hydroxide over CN minus. Okay, well, X times X over 0.100. X squared over 0.100. We're given, we can look up, the Ka value for hydrocyanic acid. We're not going to find a Kb value for cyanide, but we can calculate it from the Ka value. Remember that Ka times Kb equals Kw. Kw is a constant. Ka we can look up on a table. So the Kb for cyanide is 2.04 times 10 to the minus 5. Well, that gives us Kb. We can solve for X. X is hydroxide ion. We can figure out the POH. And if we know the POH, we can calculate the pH. Okay, so that's where we want to go from there. We're going to plug in 2.04 times 10 to the minus 5 here. We can calculate X. Since X is hydroxide, we can calculate POH. And if we know POH, we can calculate pH. The hydroxide ion is 1.42 times 10 to the minus 3. Use that to calculate POH and then calculate pH. So the negative log of 1.42 times 10 to the minus 3 will give you pH. Subtract it from 14, that'll give you pH. Since we've got 3 significant digits here, we want 3 decimals in our answer. Okay, so 3 decimal places here gives us 3 decimal places here. And because the pH is greater than 7, we're looking at a basic solution. So when sodium cyanide, which is a salt, is added to water, it's going to increase the pH. All right, so let's look at another one. Let's say that we have ammonia, NH3, and we react it with hydrochloric acid. Okay, we're going to produce ammonium ions and chloride ions, but that produces ammonium chloride. Okay, now when we break it up, we've got the ammonia, which is a weak base. We've got the hydrochloric acid, which is a strong acid, so we're going to break it up into its ions. And ammonium chloride is a salt that breaks up into ammonium ions and chloride ions. The chloride is the conjugate of a strong base. So it's not going to react in the reverse direction. But the ammonium ions will. And the ammonium ions are going to acid ionize with water. The ammonium, because it's a weak base or weak acid, is going to donate its proton to water. We're going to produce ammonia and hydronium ions. And because we increase the hydronium ion concentration, we're looking at an acidic salt. So let's say that we've got 0.100 molar ammonium chloride. Okay, well, the ammonium chloride is going to break up into the ammonium ions and chloride ions. The chloride ions are the conjugate of a strong acid, so they're not going to affect the pH of the solution, but the ammonium ions are. So we write that base or that acidic ionization reaction. So we've got the ammonium ions that are going to donate a proton to the water. We're going to produce ammonia and hydronium ions. And because we're increasing the hydronium ions, we're looking at an acid. This isn't the whole ice chart, it's just the equilibrium part. So 0.100 X and X. We can write a K expression. This time it would be a Ka expression. Okay, X times X over 0.100. And then for ammonia, it's a weak base. We can look up what the Kb value is. But because we're looking at an acid, we need the Ka value. We would take Kw and divide it by Kb. That would give us Ka. So we don't typically find Kb values for ammonia and Ka values for ammonium ions. Since they're related to each other, usually the stronger of the two is on the table, and we can calculate the other one. So now that we know the Ka, see if you can plug through the whole thing. Take Ka, plug it in here, solve for X. Now X is hydronium, so we can calculate the pH right from that value for X. So see what the pH of this ammonium chloride solution would be. All right, so I'm getting 7.46 times 10 to the minus 6 for hydronium. Take the negative log of that, and I have 5.127. Again, we want to use this 5.56 times 10 to the minus 10 here. We're going to multiply both sides by 0.100. Then take the square root of both sides, and that'll give us hydronium. Take the negative log of that, and that'll give us our pH. So let's look at another scenario. Let's say that we have sodium hydroxide, and we react it with hydrochloric acid. Okay, well, it's a double displacement reaction. The sodium and the hydrogen would switch places. We'd produce sodium chloride and water. Sodium hydroxide is a strong base. It's an electrolyte. It's going to break up into ions. Hydrochloric acid is a strong acid. Okay, it's going to break up into ions. And sodium chloride is an electrolyte. It's going to break up into ions. So really, in this solution, we have sodium ions and hydroxide ions reacting with hydrogen ions and chloride ions to produce sodium ions, chloride ions, and water. Now, the sodium ions and the chloride ions are spectator ions. So when we look at this kind of reaction, really, it's going to be the hydrogen ions from the acid reacting with the hydroxide ions from the base to form water. When we look at sodium chloride, it contains sodium ions and chloride ions. Neither of those ions affect the acidity of the solution. So sodium chloride is a neutral salt. Sodium is the cation of a strong base. Chloride is the anion of a strong acid. And whenever that happens, the salt you're looking at is a neutral salt. So let's look at this scenario. We have 0.100 molar ammonium cyanide. Well, ammonium cyanide is a salt. It's going to break up into ammonium ions and cyanide ions. Well, here's the problem here. The ammonium ions are the conjugate acid of a weak base. So it will go through this hydrolysis process and produce hydronium ions. And cyanide is the conjugate base of a weak acid, so it will also go through this process and produce hydroxide ions. So how do we know whether it's acidic or basic? Well, what we have to do is we have to compare the Ka and the Kb values. If the Ka is larger than the KB value, then it's going to be acidic. If the KB value is larger than the Ka value, then it's going to be basic. And if the Ka value equals the Kb value, then it's going to be neutral. So if the Ka value is larger, the solution that's produced when that salt dissolves in water is going to be acidic because we're going to have more hydronium ions in the solution. And if the Kb is larger, it's going to be basic because we're going to produce more hydroxide ions. So it just depends. Is this equilibrium greater where we're producing more hydronium ions? It would be acidic. Or is this equilibrium producing more hydroxide ions? And then it would be basic. So salts are either going to be acidic salts if they increase the hydronium ion concentration. They're going to be basic salts if they increase the hydroxide ion concentration. They're going to be neutral if neither the cation nor the anion affects the pH of the solution. And both the cation and the anion can affect the pH, and we have to decide which one affects it to the larger degree. All right, so let's look at some practice problems. And we'll kind of do this step by step together. What is the pH of a 0.15 molar sodium nitrite solution at 25 degrees Celsius? The temperature doesn't have to do anything with this. And it tells us that the Ka for nitrous acid is 4.5 times 10 to the minus 4. And you're like, well, this isn't the same as this. True. It's going to give us a little bit of an indication about what to do with the problem, though. Sodium nitrite is a salt. Okay, it's got sodium as its positive ion and nitrite as its negative ion. So what's going to happen is that sodium nitrite is going to break up into its ions. Okay, so sodium nitrite breaks up into sodium ions and nitrite ions. Now, sodium is the cation of a strong base. It's not going to affect the pH of the solution. Nitrite is the conjugate base of a weak acid. And since it's a conjugate base of a weak acid, it's going to go through a basic ionization reaction. So we want to write that reaction. We've got the nitrite reacting with water to produce nitrous acid and hydroxide ions. This is why it gives us that nitrous acid Ka value, okay, because it's in the reaction. Now, we need to decide whether or not this salt is acidic or basic. So look at this reaction here, specifically this. Is our salt acidic or basic? We're increasing the hydroxide ion concentration. Okay, so it's going to be a basic salt. We're increasing the hydroxide ion, which makes it basic. So that means we're going to need to write a Kb expression. We were given Ka. So we're going to have to figure out what Kb is. So for our Kb, it's products over reactants. And I didn't write the whole thing out here. I probably should have that there. So x squared over 0.15. Now we don't know Kb. The question gave us Ka. Remember that we can calculate Kb from a Ka value by taking Ka and dividing it into Kw. So Kb equals 2.2 times 10 to the minus 11. So this is what you're going to do on your own, and let's see if you can come up with the answer. This is Kb. we're going to plug it in here. So 2.2 times 10 to the minus 11 equals x squared over 0.15. Solve for x, figure out what x means, and then calculate the pH of this salt solution. All right, so for hydroxide, which is what x equals, I have 1.8 times 10 to the minus 6. Since it's hydroxide, you're going to be figuring out the pOH and then subtract it from 14 and figure out your pH. Remember that if we have 2 significant digits in the concentration, we want 2 decimal places. So the pOH is 5.74. Subtract it from 14 and 8.26 is our pH. So we're looking at a basic solution, basic salt, because we're increasing the hydroxide ion. All right, let's look at another one. So we have 0.20 molar ammonium nitrate. And it gives us the Kb for ammonia. Again, a little bit of an indicator about what we're going to be doing with this salt. So the first thing we have to do is we have to write the dissociation of our salt, break it up into its ions. Think about what it breaks up into. It's ammonium nitrate. All right, so we've got ammonium nitrate is going to break up into ammonium ions and nitrate ions. Now, ammonium is the conjugate acid of a weak base. It's going to affect the pH of our solution. Nitrate is the anion of nitric acid, which is a strong acid. This is not going to affect the pH of the solution. It's not going to take hydrogen ions out of the solution because the hydrogen ions are not going to stick to the nitrate and make nitric acid. So we want to use the ammonium. And also they kind of gave us a little bit of an indicator about that here when they gave us the Kb. So the next thing we want to do is write down the acidic ionization for the ammonium. So we've got ammonium reacting with water. Remember that hydrogen ion is going to go from the ammonium to the water. We're going to produce ammonia and hydronium ions. Because we did the last problem together, let's see, now that the kind of chemistry is written down there, let's see if we can follow through with the math. Since we're producing hydronium ions, we're looking at an acidic salt. We want to write a Ka expression because we've got hydronium here. Hydronium means Ka, hydroxide means Kb. So we're going to write a Ka expression, plug in our numbers. We're given Kb, we have to figure out Ka for our Ka expression. Calculate X. X in this case is hydronium. Calculate the pH. Let's see if you can do it. And again, when I typed these out, I was doing it, I guess, fast. I really should have the concentration of hydronium or ammonia times the concentration of hydronium divided by the concentration of ammonium before I do this part here. Kind of skipping some steps on the slide. It's a Ka expression. You have Kb given to you. You can calculate Ka from Kb. Okay, so I'm getting 5.56. That probably should just be 5.5. There's only 2 significant digits, or 5.6, sorry. 5.6 times 10 to the minus 10. Plug that in for Ka, solve for X. And when you solve for X, that's going to be hydronium. Figure out your pH. I'm getting 1.1 times 10 to the minus 5 for the hydronium ion. Take the negative log of that. 4.98 for my pH. Sometimes the salts are the harder types of questions because you have to kind of figure out what's going through this second step before you can decide whether it's an acidic salt or a basic salt. All right. So now we're not really going to do so much math. We're just going to look at kind of relationships. So we want to arrange the following 1 molar solutions from lowest to highest pH. So think about that. Lowest pH means it has the highest hydrogen ion or hydronium ion concentration. Okay, it's the most acidic. Highest pH means it has the lowest hydronium ion concentration or the highest hydroxide ion concentration. So it's basic. So let's just look at these generally first. Hydrobromic acid is a strong acid. Sodium hydroxide is a strong base. Ammonium chloride is a salt. And since it has ammonium ions in it, it's an acidic salt. Sodium cyanide is a salt. And since it has cyanide ions in it, it's a basic salt. Ammonia is a weak base. Hydrocyanic acid is a weak acid. Sodium chloride is a salt, and it's a neutral salt. And hydrofluoric acid is a weak acid. So those are the kinds of things we have to think about. The strong acid is going to have the lowest pH. And the strong base is going to have the highest pH. Okay, so we know that this is going to be first and this is going to be last. The sodium chloride is a neutral salt. So that's going to be, somewhere in the middle. Sodium fluoride is an acid. It's just a weak acid. Okay, so it's going to be on the lower side of the pH scale. Hydrocyanic acid is a weak acid. It's going to be on the lower end of the pH scale. Ammonia is a weak base. It's going to be on the higher end of the pH scale. And then we have 2 salts. Okay, this is an acidic salt. This is a basic salt. So let's look at the acidic first. Hydrobromic acid, hydrofluoric acid, hydrocyanic acid are all acids. Okay, they're all going to have low pHs. Now, the hydrobromic will have the lowest pH. If we look at the Ka values, hydrofluoric acid is a stronger acid than hydrocyanic acid. So hydrofluoric acid would have the next lowest pH. Hydrocyanic acid would be a little bit higher on the pH scale. And then ammonium chloride is an acidic salt. So it's going to have a pH less than 7, but it's going to be closer to 7 than the other ones are. So hydrobromic, hydrofluoric, hydrocyanic acid, and ammonium chloride. Now, when we look at the bases, sodium hydroxide is the strongest base, so it's going to have the highest pH. Ammonia is a weak base, so it's going to have a high pH, not as high as the strong base, but it's going to be higher than anything else. And then the sodium cyanide is a salt that is acidic in solution, so it's going to have a pH greater than 7. And then sodium chloride. So if we want to order them, hydrobromic acid would have the lowest pH, followed by hydrofluoric, which is a weak acid, followed by hydrocyanic acid, which is a weaker acid, followed by sodium chloride, which is neutral, followed by sodium cyanide, which is a basic salt, followed by ammonia, which is a weak base, and then finally sodium hydroxide, which is a strong base. So there's no math, it's just identifying what's an acid, is it a weak acid or a strong acid? What's a base? Is it a weak base or a strong base? What's a salt? Is it an acidic salt, a neutral salt, or a basic salt?